This video is about the properties of the stars. Before I get into the details of each property, let me introduce the topic of star properties in general. By the end of the star properties chapter, you will see there is an internal consistency of star properties and that these points of light are very different from the other points of light that wander among them, the planets. Once we were able to measure the distances to the stars, we found that they are very luminous compared to the planets. They are like our sun. We also discovered that there is a depth to our universe. The stars are not all at the same distance from us. And we found that the universe is a lot bigger than we thought before. The stars are very luminous things like our sun, but are they really like our sun? Are they hot like the sun? Temperature measurements show us that the stars are hot compared to the planets and more like the sun. The red ones are cooler, only 2500 to 3500 Kelvin. The yellow ones are 5000 to 7000 Kelvin. The white ones are 9000 to 15,000 Kelvin, and the blue ones are 20,000 to 50,000 Kelvin. Well, are the stars large in diameter like the sun? Size measurements show that the stars are big compared to the planets. They are large like the sun. Things that are big and hot should also be massive like the sun if they are like the sun. Mass measurements show the stars do have a lot more material in them than the planets and are more like the sun. This chapter is the most math intensive of the chapters in this book. Chapter 5 about gravity is the next most math-intensive one. But remember to keep your eye on the bigger picture, how we know what we know, and don't get bogged down with the formula. The layout of this chapter is similar to the order of the planet properties presentation. In order to compare the planets with each other and with our home planet Earth, you need to know their distances. In order to compare the stars with each other and with the sun, you need to know their distances. Finding the distance to any object in the universe is a crucial first step in discovering what it is like. Like we did with the planets, we're going to use triangulation, or the surveyor's method that has been used for thousands of years to measure big distances here on Earth. Remember when I had you look at your thumb when it was close to your face and then far from your face in the history chapter? When you look at something from two different vantage points, the object appears to shift positions compared to the far-off background. That angular shift is the parallax, and the distance between the two vantage points is the baseline. Knowing those two things, you can use trigonometry to find the distance to the object. So this method is also known as the trigonometric parallax method. An object at a greater distance has a smaller parallax. If the distance to the object is too great to measure a parallax, then we make the baseline bigger. For the planets, the baseline was the diameter of the Earth. The stars are much too far away for this tiny baseline. We need the biggest baseline we can get, which is the Earth's orbit. A picture of a nearby star is taken against the background of stars from opposite sides of the Earth's orbit, 6 months apart. In the trig parallax formula we'll be using, the parallax angle P is 1/2 of the total angular shift. At the bottom, you see where the first vocabulary word comes from. A parsec is the distance of an object that has a parallax of 1 arc second, which turns out to be a little over 3 light years. So a parsec is like the distance unit of a yard, and a light year is like the distance unit of a foot. Since we're working with the Earth's orbit as the baseline, 1 parsec equals 206,265 astronomical units, and the closest star outside the solar system is 1.3 parsecs away. Let's look at a more realistic star parallax triangle than the animation and go through an example parallax to distance problem. When I show the picture of the more realistic star parallax triangle on the dome, the Earth and the Sun are about 3 inches apart. On that scale, the nearest star would be 12.7 miles away, or from the planetarium to Nord Avenue. That's about 3 miles beyond Allen Road. Even the nearest stars are hundreds of thousands of times farther away than the planets are. That is why we can say to very great accuracy, the sun to star distance equals the planet to star distance, where the planet could be any planet in our solar system. Let's look at some examples of going from a parallax measurement to deriving the distance. Observing from Earth, the distance in parsecs equals 1 over the parallax. So if the parallax is 2 arcseconds, the distance is half a parsec. If the parallax is 1/5 of an arcsecond, the distance is 1 over 1/5, or 5 parsecs. You just flip the parallax angle over to get the distance in parsecs. Well, what if you're not observing from Earth, but say at Pluto? The distance in parsecs equals the baseline divided by the parallax. Pluto's orbit is about 40 times larger than Earth's, so it has a baseline 40 times larger. That will make the parallax of the star 40 times bigger than if we observed from Earth. If the parallax observed from Earth is 1/5 of an arcsecond, then the parallax observed from Pluto is 40 times bigger, or 8 arcseconds. The distance in parsecs for that star as seen from Pluto will be 40 divided by 8, which equals 5 parsecs. And that's the same distance we found when observing from Earth. The sun to star distance equals any planet or dwarf planet to star distance. Remember the scale model I told you at the beginning of the semester. If Pluto's entire orbit could be placed inside a quarter, the nearest star would be 80 meters away. That is from the center of the planetarium to just inside Forum East. For objects too far away for us to measure a parallax, we need to use the inverse square law of light brightness. A star looks fainter the farther away it is in a nice, predictable way. Because light spreads out with the square of the distance, the number of photons you receive is inversely proportional to the square of the distance. The apparent brightness equals the reference brightness multiplied by the square of the ratio of the reference distance over the new distance. Don't forget to square the distance effect. Notice that the brightness of stars works the same way as gravity does. When finding a star's distance, the question is, how far away is the star to appear as dim as it does? Next slide. This slide describes the magnitude system, which quantifies the brightness of an object. It is the system used in all star charts, including the ones in the back of your student guide. Developed back in the time of the ancient Greeks, it has been refined and precisely quantified for today. The main thing I want you to know about magnitudes is that the lower the magnitude, the brighter is the object. Negative magnitudes are really bright. The rest of the slide describes more details of the magnitude system. One magnitude interval corresponds to a ratio of 2.512 in actual brightness. For every one magnitude you subtract, the brightness ratio increases by about 2.5 times. For example, a 5th magnitude star is 2.512 times brighter than a 6th magnitude star. A 2nd magnitude star is 2.512 times brighter than a 3rd magnitude star. A 1st magnitude star is 2.5 times 2.5 equals 6.25 times brighter than the 3rd magnitude star, etc.